All right, so just a quick disclaimer again, everyone. For the volume examples, I don't have enough time, so I will only work with the 2D images. I'll try my best to make the 3D image, but it's not going to look nice. I promise you. I'm not good at this part. What we want to do is first sketch our, when you're trying to solve these volume problems, first make a sketch, even if it's just on a Cartesian plane, on the XY axis, right? So let's say here's my Y axis. And let's say here's my x-axis. When you make the sketch, it gives you a clue on which rule, which formula to use. So for the first example, we have y equals the square root of x, where its graph would look something like this shown in red. Okay, so in red, I have y equals square root of x. It's bounded by, the region of interest is bounded by the x-axis, which is defined as y equals 0. So here in purple, I have y equals 0, which is again the x-axis. And the vertical line, x equals 3, right? So there should have also been x equals 0 and x equals 3. So here's x equals 3. Now, notice that your curve, y equals the square root of x, it intersects with the vertical line x equals 3. If you want to figure out what's the coordinates for that point, the coordinates will be 3 comma square root 3, right? When x is 3, the square root, the y value will be the square root of 3, okay? All right, so how do I make my graph here? Well, the problem says that we are rotating this around the x-axis, right? So my bad, I was trying to do something there like that looks 3D, but it's totally not. Okay, so the way that I make my graph, by the way, or try to show that I'm sort of have like a volume problem, is I reflect the y equals the square root of x around or about the x-axis, okay? So the curve that I have in red, I am trying to reflect this over in dotted lines here. I'm rotating it over the x-axis. So when x is equal to 3 here in this dotted region, this point would be 3 comma negative square root of 3. All right. So let's think about our rotation now. If you look at the rotation, if you're rotating this, right? What do I essentially have here? Say it again. We have a bowl. Sort of look like I have a bowl. Sort of look like an acorn, right? Bowl / acorn. So what method do you think I could use? A disc, a washer, or a shell? You could use not a shell. You could use a shell maybe, but no. Say it louder. You could use either a disc or a washer. In this problem, we can use a disc or a washer because if you look at each of our discs and you look at the x-axis, the disc and the x-axis is perpendicular. So anytime that you have that the axis of rotation, and whether you're dealing with a disc, sort of like your disc there, the rotation part, and your x-axis, or whatever axis you're dealing with, if it looks like it's perpendicular, then you use the disc or the washer, right? So this implies disc / washer. Now I can use either or. If I use either or, I still get the same answer, right? By the formula for disc, right? If I use the disc formula, it says that the volume V is equal to pi times the or pi on the outside of the integral a to b of r of x dx, where r of x, this capital R, is essentially your radius. The radius of this problem is basically going to be the region between the x-axis and your curve. That region, sorry, let me just make a quick erase here. Your radius is essentially this distance. your R. And what happens here is that R depends on the square root of x. Okay? Each disk that I made, the radius depends on the square root of x. So for the volume, we say that V is equal to pi from 0 to 3 of R of x, which is the square root of x, dx. Now, one thing that I forgot to do because I was thinking of both methods, in your disk method, you have to say R squared. Okay? So what I really have is the square root of x raised to the second power dx. And you can simplify this, right? You can simplify this by saying that your volume V is equal to pi times the integral from 0 to 3 of the square root of x squared, which is just x dx. And you can get a solution, right? If you compute the volume, what is the antiderivative of x? Say again. X squared over 2 from x equals 0 to x equals 3. So, well, we can say that our volume, right, by fundamental theorem of calculus, is equal to pi on the outside times 3 squared over 2 minus 0 squared over 2. Now, what happens to the 0 squared minus 0 squared over 2? Say again. 0. So we have 3 squared over 2. What's 3 squared over 2? 9 over 2. So volume is equal to 9 pi over 2. And that's your solution using the disk method. You could have also used the washer method, right? When you're using the washer method, essentially you should see sort of like a hole in your disk, right? For example, here's my disk. But the washer, you should see some sort of hole, like a donut, right? The washer looks like a donut. Essentially what's happening is that x-axis, if you want to apply the washer method, is going to go through your disk, right? If the x-axis is going through your disk, right? What is the x-axis? What is the equation for the x-axis? What is it equal to? What is the equation for your x-axis? No, what's the equation that represents the x-axis? Y equals 0. So when I apply my washer method now, so I'll write out the formula in a second. For the washer method, you need an outer radius and an inner radius. The outer radius is going to be the square root of x, but the inner radius, since it's the square root, since the x-axis is going through your disk, essentially, to create this donut, then the x-axis is the inner radius. But the x-axis is defined as y equals 0, or simply put, 0. So your washer, the formula for it is volume equals pi times a to b of capital R squared of x minus little r squared of x dx. So it's the outer radius minus the inner radius. But in this example, your inner radius is going to be 0. If I do 0 squared, what's 0? Say it again. If the inner radius is 0, then what's 0 squared? 0. That's going to go away, and you're left with r squared, capital R, the outer radius squared, and the outer radius, I said it was defined as square root of x. So you get the same thing, right? So this here, I was going to set up the equation, but I'm not going to evaluate it. It's going to be pi from 0 to 3 of square root of x squared minus 0 squared dx, but that's still the same thing. All right. Any questions with example one? Huh? It says to not evaluate. I'll still do a little bit of evaluation. I'll do one more problem with evaluate. I'll do one more problem with evaluation, but then if it says do not evaluate, do not evaluate. End of story. End of story. You stop at 9 pi over 2 because I evaluated. But if you don't, then you stop at the first line, or second line. All right, second example. Our second example is y equals the square root of x, y equals x squared, y equals 0, and rotate around x axis. First of all, before I could even make I could make my graph. But first thing is, just like in an area problem, what do you want to find? If it gives you two curves, what do you think you got to find? Say again? I said we're not drawing the graph at the moment. What else do you think you need to find if you're given two curves? Huh? Point of intersection. That's right. So first, let's find the point of intersection. If you want to find the point of intersection, you set square root of x equals to x squared. Well, what is the square root of x? Well, you want to solve for x here, so you square both sides of the equation. So square root of x squared is x. Then you have x squared squared, which is x to the fourth. Now you subtract x on both sides. This gives you 0 equals x to the fourth minus x. And you solve by factoring, right? What's one thing that x to the fourth and x have in common? X. So if you factor an x out, what do you have remaining inside the parentheses? X cubed minus 1 equals to 0. So you could have wrote this as two equations. You could have said x equals 0, followed by x cubed minus 1 is equal to 0. For x equals 0, that's one point of inflection. Sorry, not point of inflection, but point of intersection. Point of intersection is what I want to use. So let's think of count point. All right. So then on the other part, x cubed minus 1 equals 0. You add 1 to both sides. You get x to the third equals 1. Now, x to the third equals 1. What does that tell you about x? X is equal to 1. Right? X should equal to 1. So the point of intersection is x equals 0 and x equals 1. Now we can make a graph. Right? So visually, we have the following. So again, I'm not doing this using a 3D image, but rather I'm doing this based on a 2D image. So let's say here's my y-axis. Let's say that I have my x-axis. I'm drawing my two curves, so they both meet at x equals 0, and they both meet at x equals 1. So by the way, when x is equal to 1, both of their y values is 1. So that'll be somewhere here. All right, so here you'll have the square root of x. Here you're going to have x squared. Right, so they're not the most perfect curves. I could probably erase this one just to clean it up a little bit. But there you go. You have your two curves. All right, so in this problem, it says that, of course, the function was bounded by both of them. The x-axis, which is y equals 0, and that's our way of rotating. We're rotating on the x-axis. Okay, so here's how I complete the graph to help me answer this question. Because this graph is being rotated around the x-axis, you could reflect the region in the fourth quadrant, right? So essentially, let's say here is -1. Then you have this additional point, and now you can make two additional curves to create the region. Here's your first piece. This will be the reflection of the square root of x, right? Here you'll have the reflection of x squared. Now, because of this rotation, you're going to see that you have the following. Now, what does this look like to you as I'm drawing this? You would say a disc, but no, it's not going to be a disc. It's going to be a washer. The reason why it's going to be a washer is that when I drew this, I didn't draw it correctly. Essentially, what you should have had, right? Just trying to redraw. I'm going to try to draw at least one of it. What you're going to get is that, okay, you should have a disc that goes from, that basically touches the purple regions, no? The y equals the square root of x and the dotted lines. Now, you should have another disc that's formed by y equals x squared and its reflection, which would be this piece. So as you're doing this throughout, right? You essentially have like two discs. You have one disc that starts with y equals square root of x and its reflection. And the second disc is going to be for the x squared. Now, like I said, it gets horrible, right? As you can see there, that wasn't a good spot to use. Oh crap, what did I do here? No, bring back my stuff. All right, I just botched the whole problem. I'll just fix it back, no biggie. Yeah, I think that was the only part that was erased. Yeah, so look, I'll do it again. Ready? Bree, you ready? I'm gonna erase it. Just look again closely. You have your washer essentially is being formed by like a donut with two discs, one disc inside of another. So here you have the outer disc because of the purple regions or the purple curves. That's right. And then here you will have one for the pink. And if you do this throughout, keep pulling it for infinitely many, you see that it looks like a washer. All right, so how does the washer method work? It's the outer radius minus the inner radius. So what is my outer radius in this example? Square root of x. So it's going to be pi from 0 to 1 of the square root of x squared minus x squared squared dx. And then you evaluate the volume. However, I am not going to evaluate the volume only because I'm running low on time. Okay? I'll let you guys do it as an exercise. How about that? All right. So there I did the disc and